we're going to start into vectors, and like I said, we just end the class. Um, but vectors are really, really useful in calculus. So the assignment today is 705A 1 to 55 odd. Um, vectors have only been used heavily in mathematics for maybe the last, I don't know, 30 or 40 years. Before then, we did calculus using coordinate geometry, basically, which doesn't really mean a lot to you, but just trust me, the formulas are much more complicated and harder to do, and vectors allow us to save a ton of time in doing specific parts of calculus. So this is really to prepare you for calculus, and actually every math class you've taken up until now is supposed to prepare you for calculus. And if you don't get there, then you're going to say, why did I learn all this stuff? And the answer is, I don't know. Hey, you're here. So vectors will be your friend when you move on to calculus, especially if you move on to Calc 2 or 3. I'm not sure they show up a lot in Calc 1. It was a long time ago. So what is a vector? A vector looks like an arrow, and it has two qualities. Well, I guess three qualities. So a vector has magnitude. Magnitude is the length of the vector. Okay? And then a vector also has direction. And in this class, a vector also has position. So magnitude measures the length. Well, because we're going to find out that we don't really need position as much as we thought we did. So you'll see. So we have magnitude, and then the direction would be like the angle associated with the vector. And we've been doing angles in standard position for years now, and we might as well just use the same angle system that we used in trigonometry. So we're gonna say that this is 0 degrees, and the direction of the vector can be measured as a rotation from that positive x-axis in standard position. Okay, and then a vector also has position, meaning I can move this vector around. And eventually we realize, it's not going to take us very long, that the position of the vector doesn't really matter. So what do vectors do? One of the most common applications is velocity. So speed is how fast you are traveling. It's rate divided by time. Velocity sort of seems like that, except velocity also has a direction. So if I said I'm driving 60 miles an hour, that would be a speed. My velocity would be I'm driving 60 miles an hour on my way to Price, which is north. Okay? So we're going to learn about some of the interactions of what vectors do, and then we'll get into some story problems probably tomorrow. Okay? So first, we need to figure out what the magnitude of a vector is. And let's start with something easy. So I'm going to position my vector right here. And I'm going to say that the vector ends at -3, 4. Right there. So I would draw my vector, and I want to measure the magnitude. And vectors are usually labeled as like vector u or vector v. Those are the common variables for vectors. Yes. Did you have your hand up? Yeah, it's just the Pythagorean theorem. We build a right triangle. The bottom is -3. The side is 4. -3 squared plus 4 squared equals the magnitude squared. And we write the magnitude as the absolute value of u. That means magnitude. or it could be the absolute value of v. Okay, and they're not really absolute value marks, they're just magnitude marks. But you can see why we would use absolute value, because magnitude is always positive. Okay, so that's 9 plus 16, which is 25. Oh, sorry, this should be squared. Then what do? Take the square root, and I get the magnitude of u is 5. And that's sort of the power behind a vector. In physics, the longer a vector is, the stronger it is. So you can have multiple vectors that face the same direction, but the more, the longer the vector, the more power it has. Okay? Yeah. Yep. And I'll get into that in just a little bit. What if a vector is not centered at the origin? Okay, what if I had the start of a vector is 2 comma negative 3, and the end of the vector is at 6 comma 8? So 2, negative 3, and then right here, and this is my vector. The distance formula, which is basically the Pythagorean theorem. Once again, I draw a right triangle, and I want to know how far is it from here to here. Well, that would be 6 minus 2, right? So 4. And how far is it from here to here? 11. Negative 3 to 8 is 11. How did we get those numbers? I subtracted them. I did x minus x, and I'm going to square it, plus y minus y, and I'm going to square that, and that will equal the magnitude of u squared. So then I take the square root. Now, does it matter which x I subtract? I did 6 minus 2. Does it have to be that way? No, because we're going to square it, which will get rid of that negative, right? If I did 6 minus 4 squared, 4 squared is 16. But if I do 2 minus 6 is negative 4, and negative 4 squared, it's still positive 16. So the order of the x's is not important, which means the order of the y's is not important. Does the order of the x and y matter? No. So you can't really screw this up. It's just x minus x squared plus y minus y squared, and then you take the square root. So I want the square root of 4 squared plus 11 squared. And that will tell me the magnitude squared. So I raise that to the 1/2. And the magnitude of this vector, something's not right. Oh, it is 11. I already square rooted it. Sorry. So the answer is 11.7. Okay. Everybody all right with that? So that takes care of the first one. The first set. Now I want to know a vector's direction. So if I had negative 8 comma 3, and this is written in vector notation. So vector notation uses these weird parentheses. Okay? Whenever you see that, it means a vector that starts at the origin and has an ending at negative 8, 3. Okay, that's what that little symbol means. And you can see in the first section, vectors started all over the place. And from now on, they're all going to start at the origin, because if they're not at the origin, we just move the origin and stick it where we want. Okay, it's just easier that way. I'll show you. Okay, negative 8, 3. Yep, except now I want the direction. I don't want the magnitude. I want the direction, which means I need to know how big this angle is. Okay, well, I'm in quadrant 2, and I know that in this triangle, -8 is my x, and 3 is my y. I can figure out what this angle is. The tangent of close. We've got to do a little bit of thinking here. Right. Yep. The goal is to find theta 1 and then subtract it from 180 to get theta 2. And theta 2 is our answer. Okay. But first, to find an angle, I don't use tangent, inverse tangent. And then there's something else that we need to avoid. We need to avoid the negative, because the sine will only tell me answers up here, the inverse sine. Right, and the inverse cosine will only tell me answers here, and then the tangent will also only tell me answers there. So what we're going to do is pretend that we're not in quadrant 2. So we're just going to lift this triangle out into space, forget the negatives, and then do the inverse tangent of 3/8, and I get 20.5 degrees. And now I'm in quadrant 2, which means I need to do 180 minus the answer. And I looked through the examples to see how Cynthia did this, and yeah, I don't do it her way. Okay, so we will always just lift the triangle out of the quadrant, find the angle, and then put it back in the quadrant to figure out where we are. Okay, so if I had -3, well, let's do -13, -9, that's my vector. What is the direction? Well, where am I? I'm in quadrant 3, so this would be -13, but I'm just going to call it 13. And this would be -9, but I'm just going to call it 9. So I do the inverse tangent of 9/13. Yes, because if you start plugging in negatives, sometimes you will get doesn't exist. Sometimes you get an answer that does exist, but it's in the wrong quadrant. So we will always just remove it from the quadrant and then put it back in. So I know that this is 34.7 degrees. Now I put it back into the quadrant, and I'm going to take 34.7, add it to 180. Okay, does that make sense? Okay. Oops. What about this one? I'm in quadrant 4. So 4, and this is -1, but I'm just going to write 1. So the inverse tangent of 1/4 gives me 14 degrees. What do I do with that? Subtract it from 360. Okay. And then if it gives you a vector in quadrant 1, then the inverse tangent is just the answer. Okay. So number 15, who asked about that? So all you do, you're going to have the inverse tangent of 3 over √3, and the answer you get is the answer because we're in quadrant 1. So that square root doesn't really make it any harder. Okay. Vector operations. This is one of the reasons why vectors are so valuable, is because it allows us to combine different directions and strengths into single values. So the easiest thing to do to a vector, so let's say I had the vector u, which looked like this, and you could put it in the coordinate plane if you wanted, but you don't need to. That is vector u, and let's say you're flying a drone, some kind of drone, and you are traveling in this direction at, say, 10 miles per hour. Okay? But the wind is blowing, and the wind is blowing in this direction at 4 miles per hour. Which direction and how fast will your drone be moving? Well, we do something called vector addition. And this vector, let me group those together. This vector can take place anywhere, right? Your drone can be positioned anywhere you want. But the wind direction is also taking place anywhere. So if your drone is flying in this direction and the wind is blowing in that direction, you just put you put the start and the end of one vector, start of one vector at the end of the other, and we create this new vector right there. And it actually doesn't matter which one you use. I could put this one first, and then I could put this one second, and you'll notice they end in the same place. So that red vector shows us which direction the drone will be flying because it has taken into account both forces. You're telling it to go one direction at a certain speed, and the wind is telling it to go another direction at a certain speed, and the end result is that red vector. Is that airplane flying or that drone flying faster or slower than what you're telling it to fly? Faster. How can you tell? Because, and Pythagorean theorem doesn't apply here. You'd have to do the law of cosines or the law of sines. But that red vector is longer than the vector, the original vector. So an airline that's flying across the country, they don't necessarily aim the airplane where they want to go, right? They have to aim the airplane in a direction that satisfies the wind vector that will eventually point them where they want to go. So if an airplane wants to fly from here to here, it does not aim right at the city. It's going to have to aim over here, and then the wind will make up the difference. So there's a difference between bearing and heading. Right? One says which direction you're pointed, and one says which direction you're actually traveling. Well, what if this was my flight vector, and this was my wind vector? So now I'm flying that way, which is actually slower. Yep. So, well, this is a top view. Yeah, we're looking down. So this is, um, let's say, okay. So here's Castledale, and here's Huntington. Okay. I want to fly my drone from Castledale to Huntington, but the wind is blowing. This is a really good drone. The wind is blowing in this direction, that hard. Okay? So where do I need to aim in order to land to hit Huntington? So, let me pull these down. So the wind is working that direction, so I need to fly in this direction. Yeah. So here is my resulting vector. In order to get to Huntington, I have to aim further to the left, and I have to fly stronger than I want, right? Yeah, I got to aim at Moreland and fly harder to get to Huntington. But if the wind is going in this direction that long, then I don't have to fly as hard. The goal is to hit Huntington, but I need to fly in this direction, and when you add those two vectors together, you get that. And the wind is going to help. It's going to push me along. Okay? What if I was flying in this direction and the wind was going in this direction? That's called hovering, right? Yeah. If I put more power to the drone, then I'll move forward. If I put less power, then the wind will push me backwards. Well, this is two-dimensional. We're just strictly talking two-dimensional. But but in 3 dimensions you can do vectors. So if those vectors truly were parallel, then you would fly flat. But if you're flying flat and the wind is blowing up, then you will just raise straight up in the air. Yeah. So vectors can be done 3-dimensionally. They can actually be done 4, 5, or 6, 7-dimensionally if you wanted. 3-dimensional? Oh yeah. Yeah, Calc 3 is 3-dimensional calculus. Okay. What if you just wanted to make a vector stronger? So I'm flying my drone in this direction, and I want to increase my magnitude by 20%. What would I do? So this could be, let's say, 4, 3. That's my vector. How do I increase my vector by 20%? Well, not really. I don't need the magnitude. So what can I do to each one of these numbers to increase it by 20%? Multiply it by, how about 1.2? So 4 times 1.2 and 3 times 1.2. And now my new vector is 4.8 comma 3.6. And I'm not sure what the magnitude is, but I know it has increased by 20%. So this vector is going to be, yeah, okay. So that is called a scalar multiplication. Remember when you did matrices? There were 2 ways to multiply matrices. You either multiply everything by a number, which makes them all twice as big, or you do the funny row and column multiplication. So this is scalar multiplication, where you take the numbers inside a vector and you just multiply them by 5, whatever. Now you asked about 3-dimensional vectors. This is what they would look like, 2, 3, 1. So we're 2 to the right, up 3, and off the page 1. That would be a 3-dimensional vector. Would be straight up, right. Okay. So let's say u was 3, -8, and v was 2, -2, let's say -1. What is u plus v? You just add the corresponding parts. So that would be 1, -9. Vector addition is very easy to do. Okay? What is 3v? Would be -6, -3. That, I just multiplied these both by 3. What? Oh, yeah, that won't work. What effect did 3v accomplish? It made it 3 times longer, and it did not affect the direction. So the magnitude is 3 times bigger, but the direction did not change. Okay? So that takes care of second section. What's that? We increased the magnitude by a factor of 3. Yeah. Um, So 25 through 34, or sorry, 17 through 24, you're given a u and a v, and you're just asked to perform those operations. Okay? And now find the vector given its magnitude and direction angle. So if I said the magnitude of v is 5, and my direction, what does it label? Just say theta? Theta. Okay. Theta equals 80 degrees. What is the vector? So we're in quadrant 1. Okay, this is 80, and this is 5. I need to figure out what the x and the y values of that vector. How would you do that? It's not a 3, 4, 5 because the angle's wrong. So I'm going to do the cosine. It's not a 3, 4, 5 because the angle's wrong. How many 5s are there in quadrant 1? An infinite number, right? How many of them are a 3, 4, 5? One of them, which one? The one that has the correct angle, which is like 53.1 degrees or something. So I just need to use my trig skills. Cosine of 80 is x over 5. Is that a multiply or a switch? Multiply. So 5 cosine of 80 is, oh, no, that works because this angle is only 10 degrees. So 0.868. How would I find y? Same thing with sine. 6 sine of 80, and I would expect a number, nope, 5. What would I expect my answer to be? Lots bigger. It's probably pretty close. It's got to be pretty close to 5. So 4.92. So what is the answer? V is 0.868, comma 4.92. Okay. Oh, good. Okay, what about this? Theta equals 2. Well, let's not do 2. Theta is 329, and the magnitude of u is 17. What is the vector? Well, I'm in quadrant 4, and this angle is 329, so my reference angle, so it's got to be 31. Yeah. And h is 17, so x and y. So the cosine of 31 equals x over 17. 17 cosine of 31. So x is 14.57. Then the other one's going to be 17 sine of 31. So what is my vector? 14.57, comma, no, negative 8.76, because we're in quadrant 4. Okay? That's pretty easy, right? Okay. A unit vector. So let's do an easy one first. Let's say I had the vector 3, comma 4. It's in quadrant 1. So this is 3 and this is 4. What is the length of that vector? 5, right? Now, for reasons that you won't understand yet, well, actually, that's not true. Do you remember when we did the unit circle and we decided that there are an infinite number of triangles that all have a 35-degree angle, well, 30-degree angle? and we decided that one triangle was better than all of the others. Yeah, it's called the unit circle because the hypotenuse is 1. So do you remember the sine of theta equals opposite divided by h? But if h is 1, then the sine of theta is just the opposite. Okay? So because of that, we need to know a way to make this vector length 1. So we're going to take the vector in its particular direction, and we're going to cut it off so that the length is 1. This is called a unit vector. It preserves the direction, but it either lengthens or shortens the vector until the length of it is 1. Divide it by the hypotenuse, exactly. So this hypotenuse is 5. The original vector is 3, 4. So the unit vector is 3/5, 4/5. Yeah, that's really easy. Okay, so let's say I had the vector -2, 6. So I'm in quadrant 2, -2 and 6. I want to cut it off. Where do I cut it off? Well, 6 squared plus 2 squared, that's 36 plus 4 is 40, the square root of 40, which is, does 40 have any perfect squares? 4 and 10. So the square root of 4 times the square root of 10 is 2 root 10. Okay, so -2 divided by 2 root 10, the 2's cancel. -1 over 10, root 10 over 10, comma, divide this by 2 over 10, root 10, and I get 3 over root 10, 3 root 10 over 10. That is the unit vector. So what I've done is taken this vector and cut it off so that the magnitude is 1. Okay, what if the vector is already less than 1? So let's say 1/4, -1/3. The process is the same. You're going to take, well, now it's too short. I need to lengthen it out a little bit. So 1/4 squared plus 1/3 squared equals h squared. Then I take the square root. And when I get that answer, let's say it's 1 over root 5. I don't know. Then I'm just going to divide this by 1 over root 5. Divided by 1 over root 5, and then just flip in times. So the process is exactly the same. Okay. Find a unit vector. So there's another way to label vectors. Let me see where it does the example of that. What? I don't even see it. She is. Do you guys see an IJ example? Okay, well, I'll just show it to you because I guess it's not going to show up. So one way to label a vector is this, 3, 4, or we could say 3i plus 4j. The I component is x and the y component is j, and we do that because it allows us to write an equation with different vectors in it, and the i's will only interact with the i's, and the j's will only interact with the j's. So if I had -2 comma 8 plus 3 copies of 3 comma 4, algebraically that would simply be -2i plus 8j plus 3 times 3i plus 4j. Oops, I don't need that. Like this. And then when you combine like terms, you're going to end up with something I plus something j. So the next set, all you have to be able to do is translate between those two versions of vectors. Okay? And then the last set, perform the vector operation. So this is exactly like the third set, but instead of using the vector parentheses, you're just going to use the i's and the j's. Do you want to see one of those, or do you get that? Okay. All right. Get to work.